This video is devoted to my Year 11 physics students on the topic of waves and thermodynamics. So this is the third topic in the Year 11 physics course, the preliminary physics course. And I'll start with waves 101. So a wave, it's kind of a hard thing to describe, but the best way I can describe it in layman terms, it's basically a moving disturbance that carries energy. And a very familiar example is that of a water wave. It carries energy, right? That's why you get waves. That's why surfers are able to surf, because there's motion going up and down. Okay, other types of waves are light waves, sound waves, seismic waves, aka earthquakes, gravitational waves, etc., etc. And waves, they basically come in two main types. You've got types of waves called transverse waves. So a transverse wave is basically a wave which oscillates up and down. Okay, the particles move perpendicular, so at right angles to the direction of motion of the wave. So let me draw a set of axes, x and y axes. Here's a transverse wave, looks like this. Okay, along the x-axis here, let's call that distance. Along the y-axis here, let's call that displacement. Okay, and here, where the x and y axes meet, that's the origin. Okay, it's a tilted O, if you wish. And displacement in physics is basically how far you are from your starting point, in this case, the origin. And here, that's the positive y-axis. So the displacement is positive, and here the displacement is negative, the negative y-axis. So the positive, having positive displacement means that you're moving upwards, so the wave is going upwards. Having negative displacement means that the wave is moving downwards. Okay, in this case, by definition. Okay, and it's important to note that waves, they're not physical things. Rather, it's the collective movement, the collective motion of the particles making up the substance. Okay, so along this line here, there are, think of them as little spheres, little particles. Okay, let's take this to be a water wave, for example, a water wave. Okay, it's not that it's not that there's a physical thing that's moving through the water. It's actually just the particles, the water molecules in this case, that are just oscillating, going up and down. So let's label this wave. So in physics terms, the peak of a wave is called the crest. Okay, it's the highest point on a wave. And the lowest point on the wave, the valley, if you wish, is called the trough. Okay, also known as a dip or a valley. Crest is the peak. Now, the height of the wave, okay, so the origin, it's also known as equilibrium position. Equilibrium means there's no motion, there's no movement, aka equilibrium. The distance between equilibrium and the highest point on the wave, that's called the amplitude. Similarly, the distance from equilibrium to the lowest point of the wave, that's the amplitude as well. And that's a transverse wave in a nutshell. Now, there's other things called, so basically the number of waves passing through a certain point in 1 second, that's called the frequency. I'll talk more about that in another video. Frequency, by definition, is the number of crests or waves passing a given point per second. And it's actually given the units of Hertz, named in honor of the German physicist Heinrich Hertz, who experimentally discovered radio waves in the 1880s. Okay, H and a small z in his honor. And high frequency means there's a lot of peaks. Low frequency means there's not many peaks. Okay, an analogy is so in an everyday conversation, for example, someone might say there's been a high frequency of cars in the street or on the road. That means that there's been a lot of cars. Similarly with waves, this is a high frequency wave versus this wave here, which is low frequency. So I'll leave it at that for transverse waves. Let's go on to longitudinal waves. Longitudinal. So a longitudinal wave, the best example is that of sound. So a sound wave looks something like this. And the particles in a longitudinal wave, they move parallel to the wave's direction of motion. And I should mention here as well, I'm assuming the wave to be moving this way, to the right. Okay, that's its velocity. Okay, its speed in a certain direction, its velocity to the right. Similarly here, let's assume that the wave is moving to the right. Okay, so the particles vibrate back and forth. Unlike a transverse wave, which they move perpendicular to the direction of motion of the wave. Now, where these lines are close together, very close together, these are called compressions. Compressions because the particles are compressed. So think of these lines as particles. It's just better to draw them as lines instead of spheres. So compressions, these are the squeezed together lines here. The lines that are a bit further apart, they're called rarefactions. Just think of the word rare. Rare in the sense that there's not many particles. And I should also mention, going back here, one last property, one last thing, wavelength. Okay, the wavelength, by definition, is the distance between two peaks on a wave. Wavelength. Diagram is getting a bit messy here. Wavelength is typically measured in meters. Also, the distance between two troughs is the wavelength as well. In this case, the wavelength is the distance between two compressions. Okay, and sound is an example of a longitudinal wave. Okay, sound, and it's worth mentioning, sound doesn't actually move the air. It's nothing really moving. Rather, it's the air molecules that are moving up, back and forth. And so they're the two main types of waves, transverse and longitudinal.